Hi, in this video, we are going to look at some more calculus problems. The first problem is this. Let f be defined from z to z, where z is the set of integers, and f of x is equal to x plus 3 if x is odd, and x by 2 if x is even. If k is odd and f of k is equal to 27, we want to find the sum of digits of k. So basically we have to find k given this condition. K is odd and f of k is equal to 27. And this was the definition of the function. The function is defined over integers. So either x will be an odd integer or it will be an even integer, right? So now think about it. If k is odd, from the given definition here, f of k is going to be k plus 3, right? So therefore, this condition becomes f of k plus 3 is equal to 27. Now, since k is odd, we know that k plus 3 is the sum of two odd numbers is going to be even. So f of k plus 3 is going to be having two different possibilities depending on whether k plus 3, so right, f of k plus 3 is an even number, so it will become basically k plus 3 by 2. Actually, it doesn't have two possibilities, it has a single possibility because k plus 3 is even. So f of k plus 3 is simply k plus 3 by 2, right? And therefore, our given condition becomes f of k plus 3 by 2 is equal to 27. Now we have to think of the two possibilities. K plus 3 by 2 could be even or k plus 3 by 2 could be odd. And in both the cases, we have different situations. So let's take the case that k plus 3 by 2 is even. In that case, f of an even number will be k plus 3 by 2 by 2. So by 4 is equal to 27. And you're getting k plus 3 is equal to 108. And that satisfies the condition of the problem because k plus 3, if it is 108, we have k plus 3 by 2 is 54, which is even. So from here, you're getting k is equal to 105, right? From the other condition, if k plus 3 by 2 was odd, f of k plus 3 by 2 would be simply, I will do it here, it would be k plus 3 by 2 plus 3 is equal to 27. So you are getting k plus 3 by 2 is equal to 24, but k plus 3 by 2 was supposed to be odd, so k plus 3 by 2 cannot be 24. So this is a contradiction at this step, right? So the only possibility for us is the even choice of k plus 3 by 2, and we got the value of k as 105 from there. So the sum of the digits of k is going to be 1 plus 0 plus 5, which is 6. So that finishes off this problem. A simple problem, but you have to think a little bit about how to split the function that is given, right? Let's go on to the next one, problem 103. And here we have let f be a function from a to be an onto function where a is equal to 1, 2, 3, 4, b is equal to abc. If f of 1 is equal to a, then find the total number of such functions. Find the total number of such functions. Basically, total number of onto functions which satisfies this condition, right? Okay, so let's think about it. You have a set like this 1, 2, 3, 4, and b set like this a, b, c. we already know f of a1 is equal to a. This is my A set, this is my B set. Now, first thing that we will do is find the total number of possible functions. Find the total number of functions that are possible between the two sets that are possible. So here we are not thinking about into or onto, we are just counting the total number of possible functions. One of the inputs has already been linked to an output. So f of 1 is already given as a, right? Now you have to decide what happens with 2, 3, and 4, right? Since there is no restriction, 2 could have been A, 2 could have been B, 2 could have been C. So there are 3 choices for 2. And similarly, there are 3 choices for 3 and 3 choices for 4. So the total number of choices is 3 into 3 into 3 or 27. This is the total number of functions without any restrictions. And now we will try to do a count of the number of onto functions. Okay. So let's think of how we do this count of onto functions. So we will do it by doing total number of functions minus number of into functions. That will give us the number of onto functions, right? So let's think about it. Number of functions is 27, and now we have to count the number of into functions here, right? So how do we count into functions? Remember, we have already been given f of 1 is equal to a, right? So if f of 1 is equal to a, if it is an into function, you will be having some element of the codomain that will not have a pre-image in the domain, right? That's how we understand an into function. So either B or C will not have any pre-image, right? We'll take it case by case. We will take case 1, we'll count the number of into functions where one element of B set is missing, right? So, or is not linked. We should not say is missing. We should say is not having a pre-image in A, right? So out of B and C, we cannot have A has already been linked to 1, right? So you have to select that one element out of these two. So there are two choices for it, 2C1. Let's say we have selected B, and B is the element that will not be linked to anything, right? So now you have to do 2, 3, 4, and for 2, 3, 4, you have two choices, A and C only. You cannot link them to B, right? So there are two choices for 2, there are two choices for 3, there are two choices for 4. Basically, they can be linked to A or C, A or C, A or C, right? So this is basically going to come out to be 16. 16 functions are there which have missing B element, right? The B is not linked to anything. However, this is an overcount, and we have to think about the case. We have to think about the case that uh, all the elements were linked to A only, right? So basically, we should count it like this, 2C1, and we have 2 to the power 3, which is this 2 to the power 3, but we have overcounted the case where all our elements are linked to a single element A, right? So this is the number of functions that are there which are just missing B. And we have excluded the one function where all the elements are going to a single element, right? And then case 2 is that case. Case 2 is that case where you have 2C2 and there is one way. So basically, I don't want to exclude the function where all the elements are pointing just to A, right? So this is the other into function that is possible. And here, both the elements B and C are missing, right? So the number of onto functions becomes for us 27 minus, we have 2C1, 2 cube minus 1 plus 2c2 into 1. What is this? These are the types of functions where either b or c is missing, and there are basically 14 such functions. 14 such functions where either b or c are missing. And this is the one function where both b and c are missing, right? So you can even list out the whole thing because it's such a small set. So eventually you're getting 15 functions which are there, which are into. Therefore, the number of onto functions becomes 27 minus 15, or is equal to 12. So that becomes our answer for this problem. This is the number of onto functions that we have here. You have to think of it in a case by case manner and exclude one of them and try to count what are the possible functions. And you have to double that because you could have excluded C also, right? But you have to not subtract the same case multiple times, the case where both B and C are excluded. That case you have to discount, right? Because you will do that separately here. So that becomes your answer to this problem. Let's move on. This is problem 104. The question says a polynomial of sixth degree f of x satisfies f of x is equal to f of 4 minus x for all x belongs to real. If f of x is equal to 0, has 4 distinct and 2 equal roots, then find the sum of roots of f of x. Find the sum of the roots of f of x. Okay, so basically we have a 6th degree polynomial. We are supposed to have 6 roots for it. The condition has been given that f of x is equal to f of 4 minus x for all x belongs to real, right? Now, it has also been said that there are 4 unequal roots and 2 equal roots of this polynomial, right? So let's say, let alpha be a root of f of x equal to 0. That implies f of alpha is equal to 0. But from the condition, we have f of alpha is equal to f of 4 minus alpha. So since f of alpha was 0, we also have f of 4 minus alpha is 0. Therefore, we can say if alpha is a root, then 4 minus alpha is also a root, right? Now, these are 2 distinct roots, let's say, right? Similarly, the question has said that there are 4 distinct roots. So if another distinct root was beta is a root, you would get another root 4 minus beta by the same logic. So far we have found 4 roots: alpha, 4 minus alpha, beta, 4 minus beta. And then there are 2 equal roots. Roots will be equal if alpha is equal to 4 minus alpha, which implies alpha is equal to 2. So then there will be 2 roots at 2 and 2, right? The only way in which roots are equal is if alpha is equal to 4 minus alpha, which means alpha is 2. So our 6 roots are these: alpha, 4 minus alpha, beta, 4 minus beta, and then 2 and 2, the 2 equal roots. Therefore, the sum of the roots, you can see, sum of every pair of these distinct roots is 4. This is 4 and this is 4. So the sum of the roots of f of x equals 0 is 12. So that solves this problem really quickly. Notice this trick. Even though we don't know the function, we just realized that the property f of x is equal to f of 4 minus x ensures that the roots have this pattern, that they are alpha and 4 minus alpha, beta and 4 minus beta. And after that, we are able to quickly solve the problem, right? Okay, let's look at the next problem. If the normal to the curve x is equal to t minus 1 and y is equal to 3t square minus 6 at the point 1 comma 6 makes intercepts a and b on x and y axis, we have to find the value of a minus 12b. Okay, so a simple question, we will just find the equation of the normal to this curve. So usually slope of the normal will come by this method. This is the slope of the tangent. So slope of the tangent is equal to dy by dt divided by dx by dt. So dy by dt here is simply 60 and dx by dt is 1. So slope of tangent is 60. So slope of normal would be equal to minus 1 by 60. Okay. So the point is 1 comma 6. So by parametric method, we can say t minus 1 should be 1 and 3t square minus 6 should be 6. So this implies that t is equal to 2. And notice that t is equal to 2 fits this also. So t is equal to 2 is the parametric point, and therefore the slope of the normal at this point is coming out to be minus 1 over 12, right? So equation of the normal now we can write because we know the slope and we know the point, right? So equation is y minus 6 is equal to minus 1 by 12 x minus 1. So now multiply by 12, 12y minus 72 is equal to minus x plus 1. You have 12y plus x is equal to 73. And you have x by 73 plus y by 73 by 12 is equal to 1. So therefore the intercepts are a is equal to 73 and b is equal to 73 by 12. And now we can find a minus 12b. And a is 73 minus 12 times b, which is 73 by 12. So a minus 12b is going to be equal to 0. So a very straightforward problem, simple problem on parametric differentiation. So you should be able to do that. Let's move on to the next one. This question says, let f of x be a non-constant, twice differentiable function defined on R such that it is symmetric about the line x is equal to 3, and we are given f dash half is equal to f dash 2 is equal to 0. The question is asking us for minimum number of zeros of f dash x times f triple dash x plus f double dash x whole square equals 0. The question is asking us for the minimum number of roots of this equation. The equation is f dash x times f triple dash x plus f double dash x whole square is 0. So let's start by exploiting the condition the function is symmetric about the line x is equal to 3. So that means f of 3 plus x should be same as f of 3 minus x, right? That is the meaning of symmetry. Using this condition, if I differentiate both sides of this equation, we will get f dash of 3 plus x is equal to minus f dash of 3 minus x, right? Now here, if I put x is equal to 0 here, I get immediately f dash 3 is equal to minus of f dash 3, which implies that twice f dash 3 is 0. So f dash 3 is coming out to be 0, right? So far I know that f dash half is equal to f dash 2 is equal to f dash 3 is equal to 0, right? Now in the same condition, if I put x is equal to 1 here, I will get f dash 4 is equal to minus of f dash 3 minus 1, 2. But notice that f dash 2 was already 0, right? So this is 0. So this implies that f dash 4 is also 0, right? And then we can also take advantage of the half condition and we can get a half here somehow. So how do I get a half here? We have to put x is equal to 5 by 2. So you'll get f dash 3 plus 5 by 2 is equal to minus of f dash 3 minus 5 by 2. So that implies that f dash 11 by 2 is equal to minus of f dash half, and f dash half is anyway 0. So we are getting f dash 11 by 2 is 0. So we are getting this also. So basically we have found 5 points where the derivative is vanishing. The points are half, 2, 3, 4 and 11 by 2, right? So after this, we can't do anything more. We have used the condition for f dash 2 also, and we have used the condition for this also. No matter what you do, you're not going to get new points where f dash x is 0 with this much information. So right now what I know is f dash x equals 0 has 5 roots, at least 5 roots, because there could be other roots, we just don't know. And these roots are half, 2, 3, 4, 11 by 2, right? So now we know that f dash x is equal to 0 has minimum 5 roots. So f double dash x equal to 0 has minimum 4 roots. This is coming by Rolle's theorem. Between any two roots of f dash x, there is a root of f of x, right? So if f dash x has 5 roots, there are minimum 4 roots of f double dash x. Now let's look at the expression that we had. The expression was f dash x triple dash x plus f double dash x whole square is equal to 0. Now if you think about this, this side is the derivative of what function? F dash x f double dash x, right? The derivative of f dash x and f double dash x is equal to this only. If you do chain rule differentiation, you will get this. So we are getting this is equal to 0. Now I know that f dash x has minimum 5 roots and f double dash x has minimum 4 roots. So the product f dash x f double dash x has greater than equal to 9 roots, right? Minimum 9 roots. So the derivative of that function f dash x and f double dash x will have greater than equal to 8 roots. So we can be assured that at least 8 roots are going to be present for this equation. So that is our answer for this problem. The number of roots at least has to be 8. Okay, let's look at one final problem. 1 second, I will just check the question number. Okay, so problem 107. So this is a slightly more advanced question. So this says let f of x and g of x be non-constant, continuous and differentiable real valued functions on R if for every xy belonging to R we have f of x plus y is equal to f of x times f of y minus g of x times g of y, and g of x plus y is equal to g of x f of y plus f of x g of y. We also have f dash 0 is equal to 0. Then find the value of this expression, f of 100 power 6 minus f of 100 power 4 g of 100 power 2 minus f of 100 power 2 g of 100 power 4 plus g of 100 power 6 minus 1 whole thing divided by f of 100 square and g of 100 square, and the whole thing is raised to a power 2. So don't worry about this evaluation. Right now our focus is to find out information about f of x and g of x. What can we find out about those two functions? So from the given information is this functional equation, this one and this one, right? And these are non-constant, continuous and differentiable real functions on R, right? We will look at what this comes out to be later. So let's start off by putting x is equal to y is equal to 0 in both the functional equations. So what we are going to get is f of 0 is equal to f of 0 square minus g of 0 square. And from the second one, we are going to get g of 0 is equal to 2 times g of 0 f of 0, right? Now, there are two variables here. Let f of 0 be equal to a and g of 0 be equal to b. So our equations are a is equal to a square minus b square and b is equal to 2ab, right? So from here we are getting b into 1 minus 2a is 0. So b is 0 or a is half. And if a is half, let's see what happens. If a is half, you get here half is equal to 1 by 4 minus b square, and you get b square is equal to minus 1 by 4. So this is not a real value. So a is half is not allowed. So b is 0. And if b is 0, you're getting a is equal to a square and a is equal to 1 is a possibility, right? So we are going to take a is 1 and b is 0. These are the two values. So we know basically f of 0 is 1 and we know g of 0 is 0 and we also know f dash 0 is 0. These are the three things we know right now, and then we'll proceed with the functional equations. So let's write f dash x as limit of h tends to 0 f of x plus h minus f of x by h, and now use the functional equation here. For f of x plus h, I can write f of x, f of h minus g of x and g of h minus f of x divided by h. So we are getting f dash x is equal to limit of h tends to 0. We can take f of x common here and we are getting f of h minus 1 by h plus minus of x minus 1 by h minus g of x into g of h by h, right? Now we know already that f of 0 is 1 and g of 0 is 0. So this part of it is basically f of h minus f of 0 by h, and you have a limit h tends to 0. So that is going to be basically the derivative of f dash 0, right? So this is f dash 0 by definition. So f of x into f dash 0 minus here we can write g of x into limit h tends to 0 g of h minus g of 0 by h. So this is g of x into g dash 0, right? So we are getting this expression for f dash x. F dash x is this. But we already know that f dash 0 is 0. So this part is going to vanish. So this implies we are getting f dash x is equal to minus gx and g dash 0. This is the condition we have, right? This is coming from the first differential functional equation. We have do the same process for the second functional equation also. So we can do the same thing. G dash x is equal to limit of h tends to 0, g of x plus h minus g of x by h, and apply the functional equation for g of x. G of x plus y was equal to g of x f of y plus f of x times g of y, right? So you apply that here, and after a little bit of simplification, just like we did last time, we are going to end up with this. G dash x is equal to g dash 0 into f of x. I have skipped some steps here, but you can fill up the details just like we did for f dash x. So we have f dash x from the previous screen was equal to minus g dash 0 minus g dash 0 g of x, and we have here g dash x is equal to g dash 0 f of x. So now what we will do, since both of the functions g of x and f of x are non-constant, so the derivatives cannot vanish, so g dash 0 cannot be 0, right? Because the derivatives cannot vanish, right? So now what we will do is combine these two equations together. How do I combine them? I'll multiply by g of x here and multiply by f of x here. So you will get this. G of x, g dash x is equal to g dash 0, g of x, f of x. And here you have f of x, f dash x is equal to minus g dash 0, g of x, f of x. So notice the RHS is equal and opposite. So adding these two, we get this nice result, g x, g dash x plus fx, f dash x is equal to 0. This is the result that we are getting now. So let's see what is the conclusion from here. Gx, g dash x plus fx, f dash x is equal to 0. And now if I multiply by 2 on both sides, it doesn't make a difference. And now we can say that this is the derivative of d by dx of gx square plus d by dx of f of x square is equal to 0. We are saying d by dx of g of x square plus f of x square is equal to 0, which implies that g of x square plus f of x square is equal to some constant, right? And we already found the value of f of 0, which was 1, and g of 0, which was 0. So putting x is equal to 0 here, we will get 0 plus 1 is equal to c. So therefore, c is equal to 1. So what we are getting now is that g of x whole square plus f of x whole square is equal to 1. That is the relation that is satisfied for all xy belonging to R. Notice that that pretty much tells you that these are sine and cosine functions. And the functional equations are simply formulas for sine x plus y and cos x plus y and all. And now it will be very easy to find out. We don't have to use that, but it will be very easy to find out the function that we needed to find, right? The evaluation that we had at the end. So it was something like this: f power 6 minus f power 4 g square minus f square g power 4 plus g power 6 minus 1 divided by f square g square. And all of this, f stands for f of 100 and g stands for g of 100. And the whole thing was raised to a square also. We'll first simplify the inside part. We'll write it as f power 6 plus g power 6 minus f square g square. We have f square plus g square minus 1. Notice that f square plus g square is always 1. So this part becomes 1. So this is becoming f power 6 plus g power 6 minus f square g square minus 1. And now we'll use a cube plus b cube formula here. This becomes f square plus g square f power 4 minus f square g square plus g power 4 minus g square f square minus 1. Again, this is going to become 1, and you are going to end up with basically f power 4 plus g power 4 minus f power 4 plus g power 4 minus 2 f square g square minus 1. And this can be written as 1 minus 2 f square g square. And you have a minus 2 f square g square minus 1. So 1 gets cancelled, and the numerator becomes simply minus 4 f square g square. And when you're dividing by f square g square, this gets cancelled, and you have minus 4 square, which is 16. So after solving the functional equations, it is almost obvious that the functions are sine and cosine, and then we can easily simplify. We are taking some easier symbols, f and g instead of f of 100, g of 100, and we are going to get the simplification and the answer of 16, right? So that finishes off this problem. So we looked at around 5 or 6 calculus problems in this video, and with that we have come to sort of the end for our calculus section of the problems. The next set of problems in this problem solving series will be based on algebra, and that will come from tomorrow. If you like the content, please subscribe to the channel, share it with your friends, use these problems for your revision, and I'm sure it will help you in your exams. That's it for this video. I'll see you next time.